We've talked a lot about those dilutions, and they're a pretty powerful tool. So I'm going to review some of it right now, just to see what you remember. So you guys jump in. So if we take a 30% dextrose solution, and we dilute it, so it is diluted 1:6. What is the final concentration? Well, there's actually a couple of ways we could do this. The way we've been doing is we've been using a proportion. That 1:6 dilution is set up like that, and the ratio of our percents is the same as the ratio of the dilution ratio. So the 30% is before we dilute it, so that's going to be the larger number. So that's going to go on bottom with the 6, and we cross multiply and divide. 1 times 30 divided by 6 is going to give us a 5% solution. So after that 1:6 dilution, that 30% solution is diluted down to 5%. Now another way that it could be done, and the way that the textbook often does it, is just this. They take your percent times that fraction of the dilution fraction, 1 in 5, which also gives you 6%. Like I said, I stick with this proportion because this proportion is more consistent with things we're going to be doing later on in this unit with our dosage calculations. Alternative to that, we could look at, let's say, let's ask what dilution is required to dilute a 24% solution to 3%. So again, now our dilution ratio is going to be equal to our ratio of concentrations. Remember, it's always going to be the old on bottom and the new on top. So our new concentration after we dilute it is 3%. The old is the 24%. And if we reduce that ratio down, 3 over 24 is a 1 in 8. So it's a 1 in 8 dilution. One that we didn't look at is what if we have two dilutions? Let's say a 40%, a 40% solution is diluted 1 in 8, and then 1 in 2. Find the final concentration. Well, we just go through the process twice. So 1 in 8 dilution is 1 out of 8. 40 is the old percent, so that'll go on bottom, 40%. And cross, multiply, and divide. 1 times 40 divided by 8 will give us 5%. Now then, that percentage is now going to go into the bottom of the next proportion. So we're going to continue on with a 1 in 2 dilution. And as we said, that 5% is now what we're going to start with in that dilution. Now we cross multiply. 1 times 5 divided by 2 gives us 2.5% is that final solution. And now again, the shortcut, now that we've done it the long way for a day, is we could take that original 40% and we could just multiply by both of the dilution fractions. So we could multiply by 1/8 and times 1/2. 40 times 1/8 times 1/2 is 2.5. So 2.5%. The other thing we looked at was that change of concentration or concentration adjustment formula. There was the C1 V1 equals C2 V2. So as we look at that, let's say we are told that a 40 milliliter sample of 22.5% concentrate is diluted to 120 milliliters. So the 120 milliliters is the final volume. What is, or find the new concentration? So, the first concentration is the 22.5%. We could change that to a decimal of 0.225, or we can leave it as 22.5. I'm going to choose to leave it as 22.5 because then my result on the other side is also going to already be in the percent form. We had 40 milliliters is the volume of that. That has to equal our new concentration, C2, times that new volume of 120 milliliters. So we do the 22.5 times 40, which is what, 90? 900, I should say, equals C2 times 120. And we divide by the 120, which is 7.5 is C2. So 7.5% is the new concentration. We had problems using that formula where 240 milliliters of saline is added to 120 milliliters of 36% concentrate or solution. Again, find the new concentration. So our old concentration is the 36%, so we'll just leave it as 36 times the old volume of 120 equals, we're finding the new concentration, so that's C2 times our new volume, however, is the original 120 milliliters plus the 240. Because here it says 240 milliliters of saline is added to it, not that the total volume is 240 after it's diluted. So 36 times 120 is what, 4320, I believe, equals C2 times adding the 120 and the 240 is 360. And now we can go ahead and divide by the 360. And we should get 12 equals C2, so 12%. And finally, we might be asked, how much saline should you add to 60 milliliters of 42% solution to dilute it to 7%. So again, we have an old concentration and an old volume. So 42% times 60 milliliters. Now this time we have the new concentration of 7%, and we are looking for the new volume. So we have 42 times 60, which is 2,520, equals 7 times V2. And we'll divide by the 7, which should be 360 equals V2. So you would need to add 360 would be the total volume. You would need to add then 360 minus the initial volume of 60. The difference in volume is 300 milliliters, and that has to be made up with the saline. Okay, so enough review from the stuff we've covered already. Now I want to move on. Today I want to talk about these concentrations and how the concentration is found. It's not as simple as just finding a percent. There are actually 3 different types of concentration. And probably the simplest one is a weight in weight solution, concentration. The abbreviation is W/W, weight over weight. And in this case, it is the weight of the active ingredient, the serum or the solute, over the weight of the total solution. Now that will give you a concentration as a decimal, as a rate. So you got to either move the decimal point or multiply by 100 to make it a percent. So if we have 24 milligrams of medication, is dissolved into 120 milligrams of solution. The concentration there is going to be 24 milligrams, that's the medication, the solute or concentrate, over the 120 milligrams is the total solution. So the milligrams cancel out. 24 divided by 120 is 0.2, so a concentration of 0.2 or 20%. That would be a 20% solution. Now the nice thing about volumes when we're dealing, or not volumes, about weights when we are dealing with these items. And by the way, you may have noticed milligrams are a unit of mass, not weight, but we still refer to it as a weight in weight solution. But anything, the nice thing about these weights is they are additive. What do I mean by that? Well, if we combine 30 milligrams of serum of a medication with 120 milligrams of saline, it will create 30 plus 120 or 150 milligrams of total solution. So if we're looking at, let's look at that one. We combined that 30 milligrams of serum with 120 milligrams of total solution. So that's going to give us 30 over 150. Again, the milligrams cancel out. 30 divided by 150 is again 0.2 or 20% solution. So we could use this going in the other direction if we're asked how much saline should be combined with 12 milligrams of medication to create a 6% weight and weight solution. So 6% means 6 out of 100. So this is just back to our percent calculations now again. The 12 milligrams, that is the serum that would go on top. And if we cross multiply and divide here, 100 times 12 divided by 6, we get 200 milligrams down here. Now remember, this is the total, so we do still have to subtract the 12 milligrams of medication, of serum here, to get 188 milligrams of saline. So that weight and weight concentration is relatively simple. Next we have a volume in volume concentration. So just like it sounds, of course abbreviated V over V, just like it sounds, it is the volume of medication over the total volume of the solution. So here, let's say that we do 40 milliliters, we're dealing with volume, of medication is diluted into 200 milliliters of solution. So the concentration there again would be the volume of the medication is 40 milliliters. The 200 milliliters of solution is the total volume of the solution. Milliliters cancel. We divide that out. Once again, we get 0.2. I seem to be stuck in a rut on my examples today. That would be a 20% solution again. The difference here is volume is not necessarily additive. So I shouldn't say is not additive, but it might not be additive. So the might is the key word there. Generally, a volume and volume solution is used if we are combining two liquids. And when we're combining two liquids, it's more likely to be additive than if we're doing a powder into a liquid. But there are still possibilities like rubbing alcohol in water. Alcohol does dissolve into water. So when we add, 50 milliliters of alcohol, of rubbing alcohol into 200 milliliters of water, the result is not 250 milliliters. 250 milliliters would be the maximum volume, but it's always going to be less than that if it's a solution. Remember, we mentioned this a week ago, that if it creates a solution, that volume is going to be less than the total. If it's a suspension, then it will stay at that total volume. The volumes do combine, they're additive. The weight and weight up here, that is typically used, get back up to it. Weight and weight is typically used for a powder or a solid into a liquid. So it's the weight of the powder or the solid substance, then the weight of the fluid that's being dissolved into. Okay, so we might ask how much medication is needed to create 400 milliliters of 17% solution. And I should specify 17% volume in volume solution. So 17% is 17 out of 100. The 400 milliliters is the total volume, so it'll go on to the bottom. Remember, 100 always represents the total or the beginning amount. And we can cross multiply and divide. 17 times 400 divided by 100 is 68. So it'd be 68 milliliters of that medication would be required. So when we're dealing with a volume and volume medication, we cannot ask, find the concentration when 30 milliliters of medication is combined with 210 milliliters of saline. Because we don't know if that medication is going to be dissolved into that saline or not. If the medication dissolves into it, the total volume will not be 210 plus 30. It'll be less than that. So if I tell you that this will be a suspension, then we now can assume that the volumes will be additive. Now I should have asked again for a volume and volume concentration here. So the volume and volume concentration, blank over 100, is going to be 30 milliliters over 210 plus 30. So 210 plus 30 gives 240 milliliters. So milliliters can cancel out. We can cross multiply and divide. 100 times 30 divided by 240 is going to give us 12.5. So that's 12.5%. The other way we could have done is we could have just divided this out to get 0.125 and change that to 12.5%. Okay, the final type of concentration that we have is a weight in volume. The abbreviation, of course, is W/V concentration. And in a weight in volume, it is the weight of the medicine so weight of the medication over the total volume. But since we're mixing units here of weight and volume together, we need to be very careful with our units. If you recall, back when we were talking about measurement in the metric system, metric units of mass, 1 gram, note by the way, gram is just abbreviated G, not GR. GR is grain. A couple of you had mistakes on the test because you saw GR for grain and you assumed it was gram. So 1 gram is defined to be the mass of 1 milliliter of water. Since most of our medications that we give are either solutions created with water, medications dissolved in water, or fluids that are similar to water. Like I said, we've got rubbing alcohol that's slightly less dense than water. We've got glycerin that's slightly more dense than water. But on average, they're pretty close to the mass of water, the density of water. So we equate 1 gram to 1 milliliter. So when we're doing a weight in volume concentration like this, the weight must be measured in grams and the volume in milliliters. So we might ask, find the concentration. I'll catch myself here. Find the weight and volume concentration when 6 grams of medication are dissolved into 300 milliliters of solution. So this does meet the qualification. The mass or weight is in grams. The volume is in milliliters. And we'll divide that out. 6 divided by 300 should give us 2.02, which of course is 2%. So that is a 2% concentration solution. Most of the time, a weight in volume solution is a powdered medication in a fluid, and it probably is the most common that we have. And these are almost never additive. So if we say we're going to add so many grams of medication into that solution, we have to know the total volume of the solution. We cannot just know the amount of saline. To figure out the amount to constitute these solutions, what you would do is in your beaker, you would have your 6 grams of powdered medication in the beaker, and then somewhere up here you got your 300 milliliter mark. You're just going to pour in saline, get it up close to that mark, stir it really well, because after you stir it, the volume actually should go down a little bit as the medication dissolves into the water, into the saline. And then you're just going to keep slowly adding and stirring until that level gets up to the 300 milliliter mark. And it will take more than 294 milliliters of water. It may actually take all 300 milliliters of water to get that mark. 6 grams of powder, depending on the powder, might actually be able to completely hide in the water. So we might ask, how much medication is required to create 200 milliliters of 11% weight and volume solution. So 11% is 11 out of 100. The 200 milliliters is the total solutions that goes on bottom. Now here's a little bit different than many of these proportions because we know the unit on top is going to be grams. It's going to be slightly different. And we will cross multiply here and divide. 11 times 200 is 2200. Divided by 100 is 22. So it would take 22 grams of medication. Now, like I said, we cannot ask how many how many milliliters of saline are required because we don't know exactly how that's going to work out. The only time we can really ask how much saline, or how much water, how much NS is needed to create 50 grams of 30% weight in weight solution. Remember, the weight in weight is the only one that's truly additive. So it is a 30% solution, so 30 out of 100. We are creating 50 grams, so 50 grams is our total. We cross multiply and divide. 30 times 50 divided by 100 is 15 grams. Now, before we answer our question, we need to look at what this represents. Remember, the top number here represents the weight of the medication. The 50 represents the total weight of the whole solution. So to get the weight or the amount of saline required, we do have to remember to subtract. 50 grams minus 15 grams gives us 35 grams of saline is required for that solution. Okay, so the last thing I want to talk about today is I want to look at syringes. And this is basically an exercise in reading scales and dealing with scales. When we look at these syringes, the first thing we need to be able to do is to figure out what each division on that syringe stands for. So if this is marked milliliters, and this is 1, 2, 3, 4, like that, we need to figure out what each marking on here means. Now, generally, I don't start at the beginning of the syringe here. This I squared off the syringe when I made it just to make it easier. But typically, the end of these syringes bevel, and sometimes the markings might be on that, right on that bevel. It might be hard to see the first few markings. So when I'm looking at a syringe to figure out the divisions, I usually go from 1 to 2. And this is marked in milliliters, so that range covers 1 milliliter. Then I count how many divisions there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1 milliliter divided by 10 divisions means 1 divided by 10 is 0.1 milliliters per division. So each mark on that syringe is 1/10 of a milliliter. So if that syringe gets filled up with a medication, like that, my coloring skills aren't much better than my drawing skills, unfortunately. To read what volume is in that syringe, there's where we're marked at. We find the nearest number below it. This is 3, and we can count up or count the markings and multiply however we want to do it. This is 3, that's 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, and 3.7. So that's 3.7 milliliters contained in that syringe. So if I come down to this syringe here, and this one might be marked differently. So that might be marked milliliters. Might be marked like that. So this one, to figure out the divisions, again, I'll go from 1 to 2. So that is 1 milliliter. And if I count, there's 1, 2, 3, 4, 5 divisions. So each division is 0.2 milliliters. So it's 0.2 milliliters per division. If my next syringe down here is marked milliliters, and this is marked 1 and 2 like that, well, I do the same thing. I have 1 milliliter there from 1 to 2. But now I count the divisions. I've got 1, 2, 3, 4, 5, 10, 15, 20, divisions in between there. So 1 divided by 20 is 0.05 milliliters per division. Now, obviously, I've got these syringes drawn so that they are all the same width. But a syringe like this that holds 9 milliliters would obviously be much wider than the one like this that only contains, a little over 2 milliliters. It's that width of the syringe, the breadth of the girth of the syringe that allows it to change that scale. If I had a dosage that was called for of 1.8 milliliters, there's a 1.8 mark on either one of these syringes. But which one would I want to use? The top one or the bottom one? Or doesn't it matter? Well, when we're measuring, there's always a slight error. On the bottom one here, let's find the 1.8. Here's the 1. Obviously, it's between the 1 and the 2. This is 1.5. And we said each marking is 0.05. So this is 1.55, 1.60, 1.65, 1.70, 1.75, 1.80 is going to be right there. So it's 1.8 milliliters right there. On the top one, each division is 0.2. So this is 1, 1.2, 1.4, 1.6, 1.8. So 1.8 is right there. So you can see both of them have a marking at exactly 1.8 milliliters. The difference is this top one here, being a wider syringe with a higher capacity, being off by just a little bit with that plunger means quite a bit of volume. Let's say we're off by half of a mark there, which isn't uncommon, maybe not quite half a mark, but half of a mark there, half of 0.2 milliliters, that'd be off by 0.1 milliliter. When you're only dealing with a 1.8 milliliter dose, that's nearly a 5% error. Over here, if we're off by half a mark, well, half of the 0.05, we're only off by 0.025 milliliters, which is less than a 1.5% error. When we're filling a syringe, we want to fill the syringe as full as possible. So when we choose a syringe to use, we want to use a syringe where the dosage is as close to being full as we can get a syringe to match up. So here, 1.8 milliliters being up here compared to 1.8 milliliters being only here, we would definitely want to use this bottom syringe. And the main reason is a full syringe, the fuller the syringe, the less the error is. So the closer that syringe is to being totally full, the smaller the error is by being off by just a touch on that plunger. So let's say this syringe here is labeled cc's 1, 2, 3, 4. And the dosage is called for 4.2 milliliters. How do we convert 4.2 milliliters into cc's? Remember, cc's is another way of writing cubic centimeters, centimeters cubed. 1 milliliter is defined to be 1 centimeter cubed. So this occurs quite a bit, where instead of being marked in milliliters, the syringe is marked in cc's for cubic centimeters. Well, they are the same thing. So 4.2 milliliters is going to be 4.2 cubic centimeters. So on this one, we've done this one before, but I'll do it again quick. That's 1 milliliter. I went from 2 to 3 this time instead of from 1 to 2, but that's 1 milliliter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions. So 0.1 milliliter per division. So 4.2 milliliters. We're going to start at 4 and count up 4.1, 4.2. So we would fill that syringe as close as we could get to that line. Okay, it's about that time for the day. So what I'm going to have you do, we're not going to work on syringes quite yet. We'll talk about them just a little bit more on Friday. For right now, we're going to just have you deal with these solution concentrations. Page 146 in the book, 1 through 17 the odd. For those of you in Boston who are going on spring break in 2 weeks, like I said, I did send some pages out to you, but I'm going to give them to you now here as well, if I've got them handy.
She gave us the sheet with all of them on there.
Oh, she did. Okay, so I don't have to write them down for you again. Okay, good. And like I said, we may not get through all of them. We may still have the very last one to do when I get back, or when you guys get back. But we'll be pretty close to being done with all of those. We'll spend a couple of days reviewing and doing more examples of dosage calculations after that. Then we'll be jumping into a test. Okay, well, you guys have a great day, and we'll see you on Friday.
Thank you.
Thank you.